Hello, everyone. We're now starting Chapter 2 of the book. Chapter 2 is basically on the topic of descriptive statistics. It's the art of summarizing data and showing patterns that you see in the data. This is distinct from inferential statistics, where you ask yourself the question, is the pattern that I see in the data really out there in the population where the data came from, or is it just a matter of chance variation in how the data was collected? We're going to focus on the descriptive part in Chapter 2, and then subsequent chapters will bring us gradually more into the inferential part of statistics. This upcoming set of screencasts is on the first section of Chapter 2. It's how to do descriptive statistics when you're working with numerical data, numerical variables in a data set. Now, before we get started, since we're in a new chapter, it's always a good idea when you log into RStudio to take a look at what you've got up and maybe clean things up a little bit. For example, you might have a lot of files open here up in your Files pane that you don't need anymore because they're from a previous chapter. You can close them. Don't worry, you won't lose them. They're still, saved in your home directory. You can close them out now just by pressing on the little X's. And now only the console window shows. And another thing is that you might have been running some R code from the console and have created some R objects here in your global environment, and you don't need them anymore. And it's a really good idea anyway to clear out your global environment from time to time so that you don't get confused about what R objects you've created and what you haven't. So if you just press the little broom and say yes, you'll clear out that global environment. Okay, let's go ahead and open up the slides for Chapter 2, Section 1. So we head over to the dots, type in /com, Dr. White stuff, Mat 111, slides. And we want the OS 2.1 numerical data slides. Click on that, view in web browser. Okay, examining numerical data. So these slides will help you out when you look in the textbook in section 2.1, and of course they're also going to get you ready for doing the DA. You want to make sure that you have the package TigerStats attached and also OpenIntro. Most likely you do, but sometimes people have trouble with RStudio for one reason or another, and they have to start off their R session anew. And so just in case, let's copy, go to RStudio, paste into the console, and make sure those packages are attached. Great, run those commands. So you can examine variables graphically, and you can also examine them numerically. We'll look at some graphical approaches to numerical variables first of all. To do that, let's take a simple example of a data set that contains a rich variety of variables and some interesting questions to look at. And it's one that we'll use a lot as kind of a token example for much of the rest of the course. It's the M111 survey data set that's inside the TigerStats package. So you actually only need to do view and help here. I'll just copy those, and then we'll learn about the data set with particular attention to one of its numerical variables, the variable fastest. Okay, copy. Head over to RStudio. Okay, and so we've got help over here, and we've got view up here. Let's start with the help. So we can pop the help up big if we hover over that little arrow and piece of paper where it says show in new window. So these are the results of a survey that were given to all of the Math 111 students one fall at Georgetown College. Everybody got a little survey form and they answered questions. And one question asked, how tall are you in inches? And so the variable in the data frame that tells that is height. Ideal height is how tall the person ideally wanted to be. Sleep is how much sleep the person got that night. And fastest, which is the one that we're going to be most interested in right now, is what was the fastest that you ever drove a car in miles per hour. Students answered in miles per hour. Some other interesting ones that we'll look at later. How do you feel about your weight? Do you feel like you're underweight, like you're about right, or overweight? As we go through this, it might be good to think to yourself, what kind of variables are each of these? You know, like height, a numerical variable probably, right? And should be maybe continuous numerical. Same for ideal height. How about fastest? Probably another numerical continuous variable. On the other hand, weight field would be a categorical variable. Its values aren't numbers. Instead, they were underweight, about right, and overweight. And they seem to come in an order. So that would be a categorical ordinal variable. On the other hand, love first is, do you believe in love at first sight? And the answers were yes and no. And those don't seem to come in an order. So maybe we could call that a categorical nominal variable. So it's just a good idea to think about these kinds of things whenever you're learning about a new data set. What type of variables does it have in it? Here's another one down here, sex. What sex are you? And students said either male or female. So another categorical nominal variable. And they say at the bottom it says a data frame with 71 rows and 12 variables. Here are the 12 variables. The 71 rows, that means there must have been 71 students in the study. Every row would be a student, I bet. But let's confirm that. I'll click out of this view and look here in the view of the data. And sure enough, in this Excel-like presentation, every row is a student and every column is one of the variables recorded for this student. And so the first student in the data frame drove a car at 119 miles per hour, fastest they ever drove a car. Okay, so having learned about the data set, let's see what we'd like to do with it. So say we're interested in a question like this. What's the typical fastest speed ever driven by Georgetown College students? What can we learn about that from the sample that we have of these 71 students? We can investigate the variable fastest graphically in various ways, and one of them is to make a histogram of the fastest speeds ever driven. So let's take a look at this histogram here and figure out what it's telling us, and then we'll figure out how we can make histograms like this ourselves. So when you've got a numerical variable, a histogram is formed by setting up an x-axis where the values of the variable can be. And when you see the x-axis is labeled here, fastest speed ever driven, miles per hour, that's a good idea. They've described the variable carefully and said what units it is. And then along the x-axis, you see that some of the values are labeled so you can kind of tell what other values are. Here's 100 miles an hour, here's 150 miles an hour. And when you look at these little rectangles that have been formed, how many of them are between 100 and 150? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. And not quite, I think each of these rectangles is probably maybe about a little more than 5, but maybe than 6 wide, because you got about 9. You got 9 of them that go almost from 100 to 150. 9 of them going almost 50 units, and 50 divided by 9 would be more than 5, but less than 6. So each of these little rectangles is, let's just say, about 5 miles per hour wide. Now, each of these rectangles has a height, and what's going on is, if somebody's speed falls in the range between, say, the left-hand and the right-hand endpoint of one of these rectangles, they count into making the height of the rectangle. So like this rectangle here, where I'm running my mouse up and down, it goes from 100 miles per hour to about 105 miles an hour. And it seems to be about 7 high. So that's telling me that 7 people reported driving at their fastest somewhere between 100 and 105 miles per hour. On the other hand, this rectangle here, the very tall one, seems to run about 5 units, 95 to 100 miles per hour. And it's 15 high. So 15 people drove between 95 and 100 miles per hour. Now, some things that you won't get right off the histogram that you might wonder about, like what if somebody's exactly at the boundary between these two rectangles, like right at 100 miles per hour? Do they get into the rectangle on the left that's 15 high, or the one on the right that is 7 high? And the picture doesn't tell you that. And it's not meant to tell you everything precise about the data, but just to give you an idea of where the speeds are generally. And so take an overall look at the histogram. You'll see that the rectangles tend to be kind of tall, around 100 miles an hour. And then there's some really short rectangles. In fact, rectangles that look like they're about 1 high. Here's a short one at about 160, and here's another short one at maybe about 190. So there's like a person who drove about 160 and a person who drove about 190. But for the most part, it looks like most of the students, big heights here for the rectangles, they're crowded around 100 miles per hour. So this histogram can tell you that if you had to give like one number that was like a typical fastest speed, 100 miles per hour might not be bad, 105 miles per hour, something like that, something in that range. So, great histogram, how do you make it? So, you can make it with this function GF histogram, which is available whenever you load the package TigerStats. GF is short for GG formula. It's just some technical thing about a graphing package in the R language. And then there's an underscore, and then the kind of a graph you want to make, histogram. And the way you make a histogram of that specific data is you want to say what variable you're going to make the histogram from. Now, that's the fastest speeds. And that's the variable fastest, which was spelled fastest, all lowercase. To let R know that it's a variable inside a data frame, you put a little twiddles first, and then you put the name of the variable. And then you put a comma, because you finished telling the function its first input, the variable. And you always put commas between your inputs. And then your next input is going to be to tell R what data set to look for that variable inside of. And so you're telling it to look inside the M111 survey data set. And then another comma, because you're finished with that input to the function. At that point, you could really have a histogram, totally. But if you would like to make some specific choices about colors and things for the histogram, then you go on and give more inputs. Color equal black is going to tell you what color to make the borders of those rectangles. Fill equals sky blue is you're choosing a color for what's inside the rectangles. And that's how we're going to get that sky blue looking color inside those rectangles. And the way we got the nice label for the x-axis was by saying xlab equals fastest speed ever driven miles per hour. And you'll notice that all those options there, they're inside quotes. They're what are called strings, text in a computer language. And then there's a closing parenthesis to match the opening parenthesis here, and that draws all the inputs together when you're asking this function to make that histogram. So to get this code to make a histogram, you would need to copy all of it right down to the closing parenthesis. And then you can head over to our studio, and let's just give it a try in the console for ourselves. So I've copied it in, and I pressed enter. The code ran, and this nice graph popped up over here that looks like what we saw in the slides. I could get my face out of the way and you could like see it a little better. I think I could. Come on, face, move. It's not moving. Not sure why. So I'll tell you what, I'm just going to pop this graph up bigger by hovering here over zoom. And there's my silly face still. I'm going to remove my face. And so you can see the plot bigger. Actually, I'm a little bit worried that you might not be able to see that because in my screencast, I only shared my Chrome browser, and I'm just a little worried that you're not going to see this lovely pop-up. So I'm just going to unpop it and look and have you look in the lower left-hand corner. And you can see the histogram made that we looked at in the slides. So if you want to make histograms, this slide is a good reference for how to do it. I do point out that the bottom three are, they're options that make the histogram look better. They are optional, but they are strongly recommended. And note that you can change these things yourself. So let me try this again. I'm going to paste that in. But I'm going to say that I would like the color on the edges of the rectangles to be blue. And I would like the rectangles themselves to be, how about brown? And I'll leave the x-axis label alone. And see what we get. And so, to me, not as great a choice on colors. It seems a little clashy, but I'm colorblind. Who am I to really tell? But the idea is that you can actually play around with a lot of the options. You can choose many of them for yourself. I'll just tell you right here that there's a lot of colors that you could put in. If you type into the console colors, parentheses like that in the lower left, and just run that command, you will get a little output to the console of 657 color names. And you can use any one of those color names. So like you could go for deep pink 2, for example. Let's give this a try. I'm going to up arrow, getting back to colors, up arrow again, getting back to that histogram, and I'm going to try the fill to be deep pink 2. Okay, and let's run that. And sure enough, over here in the plots window, I did change the color of the fill. Another thing, just to show you that what's really optional, I'm just going to try the command again, but I'm erasing the last three inputs. So the only essential inputs are the twiddle's fastest and the data is M111 survey. If you run that function, then R does the best job it can. It wasn't given a color for the border of the rectangles, so it just kind of left that out. You can't see their borders. And it looks like there's some kind of a dark grayish color for the fill that it uses by default. And because you didn't give a label for the x-axis, it gave just the name of the variable here for the x-axis. The y-axis, R always takes care of that on a histogram. It's the count. It's how many people fell into each rectangle. Okay. There's other graphical ways to examine numerical data. One way is to make a density plot. And here you see one before you. So the idea behind a density plot is similar to a histogram in that along the x-axis stand the possible values for your variable, fastest speed ever driven. But the y-axis is something called a density scale, and it has funny numbers. You don't have to know how those numbers are made. All you really need to know is that this shaded area underneath this curve is 1. Using this scale, it's set up to be 1. 1 stands for 100%. 100% of the people in the data had a speed somewhere from between here and here. And where the density curve is tall, that's where people's speeds are more closely crowded together. And where the curve is short is where the speeds are more spread apart from each other. And so looking here, there was a person, that went around 160 and a person went around 190. They're pretty spread apart. And so the density curve is low. There must have been a lot of people who reported speeds around 100 because the density curve is high there. Now, to try to help us interpret the density plot, a rug has been added to it. The rug is this set of tick marks that you see along the bottom, along the x-axis. Every individual person's reported speed comes out as a tick mark here. Now, what happens though is if two people report the same speed, their tick marks sit right on top of each other. So like this one here at 100, I really don't know how many people said 100. There's a tick mark there, but there could be a lot of tick marks sitting on top of each other. In fact, for these speeds around here, since people tend to round off their answers to a question like this, there's probably a lot of overplotting of the tick marks. But you can still see some more crowding here than out here. Another thing about a density plot is that even when things are spread out, and even when there's like no value over it, the density plot will still have some height. Like there's nobody who drove exactly this speed here, but there's still some height here. The density plot algorithm is basically trying to do more than just tell you about the speeds that were in the data. It's trying to make a guess about what other speeds would be seen if you could have drawn a much bigger sample from the population. And so it's suggesting that there might be like a very, very small proportion of people who drive this speed here, even though nobody like that showed up in the data this time. So how do you make a density plot? Well, the good news is that it's very similar to making a histogram. You really don't have to change the code very much. Instead of GF histogram, it's GF underscore density. And for numerical data, it's the same idea. You got to say what variable that you want a density plot for. And so you use a twiddles and the name of the variable. And then you say what data set it lives in. And then there's those same three options that you can use. This time color is going to say what color to make that curve on top. And fill is how to shade in underneath. And the X label you would work with also in the same way as with a histogram. Give a good descriptive label with units. I'm just going to run this part of the code all the way down to this closing parentheses for now over in RStudio. Command C. Copy it in. And there we get our histogram. You'll see there's no rug. To get the rug, you want to add basically another graphical element into this plot. And adding new graphical elements can be done with this % bigger than % symbol. And then you say what you want to add in. And you want to add in a rug. And you want to make that rug with the fastest variable. And the fastest variable comes from M111 survey. And then there's a technical thing that you have to say to make it work. I apologize on behalf of the authors of the GF package, but you have to say inherit equals false. So if you run all of this together, so I've copied it in, there it is. Then you get the entire plot as we saw in the slides. While we're still here, I just want to reassure you that you're not going to have to memorize how to make all of these plots in all of this detail. I will teach you enough R code so that you can make these plots. I'll give you enough example R code so that you can just change them a little bit to make new plots. And I'll point you to tutorials on the web and reviews that will help you to make a new plot on your own if you have to someday. I also want to point out that there's help right here in the RStudio console. Like if you wanted to just type in a new command all on your own to make a histogram, say for the fastest speeds, you can type in GF _. By the time you get a few characters into the function, you actually get a little code completion pop-up here for all the things that start with GF _. And scrolling down, you can see histogram. And then you can say twiddles and the name of your variable. And then data equals M111 survey. Notice you can keep it all in one line if you want to. You don't have to separate it out into different lines like we often do in the slides. And then there's your simple histogram. So we've looked at two graphical ways to examine a numerical variable, histograms and density plots. You can also make numerical summaries for a numerical variable. I would like to address that in a separate screencast, so I'll see you soon.